Testing, testing, test, test.
good. I wanted to take as a mouse. Almost did. Okay. This is our new slide, right? Yeah, thank you. Oh, is it all time?
Just this. It's very strange.
Interesting noise. Hello.
It's very strange.
Test.
There's like 5 seconds left. Just start saying.
1, 2, 3.
That's much better. Yeah. Okay.
That's excellent.
So not audio input. Yes.
Okay, and there's almost no delay. That's perfect.
Okay.
Just for the recording.
Yeah, this one's like these are messed up. This thing's the only thing.
There's almost no delay.
What's that?
And I do the same thing with the start recording. Right?
Yeah. So keep it going and then start recording.
Well,
Now reports by default in MKV. Stuff at all.
yeah, well, we'll figure it out.
That's the update delay. That's flashes.
Many people registered? Okay. So, yes. So, you know elevators?
What are those?
Elevators,
Oh,
when
yeah,
you came.
yeah.
So if you continue going that way and then just on the left.
Okay, cool. Thank you.
You're welcome.
Yeah, that's the first thing. Sounds good. Okay.
Is it recorded on YouTube?
It is also, but I started it a long time ago, and editing at YouTube is almost impossible now.
Okay.
So it's better to also record. Exactly.
Okay.
Yeah, you can easily delete things, but they used to have handy tools where you could cut the pics in
Yeah.
the front and like not fancy editing, but you can still do it or tell it to do it, like on old interface, but it never does it.
But now you can just delete it and put our
With
one,
our own, exactly.
the one that's cut. Yeah. Movie. We'll just wait for the user to come back. I mean, it's only listener.
I send a reminder, but I know it's 10 o'clock. See you. So,
It's okay. Thank you. I should get it now.
The only thing I can't make work is the chat. I don't know what's wrong with the chat.
Oh, you want to Slack?
No, yeah.
Slack? Just, you know.
But he can't
Online
get on our
question.
Slack. Yeah, we have to invite him to a special.
Oh, and here chat doesn't work.
Oh, it can. Yes, let's see. This works.
What about this three thing on the... on the bottom? Come on in. You're here for intro?
Yeah.
Intro to SciNet?
Yeah,
Okay.
to SciNet.
Just, let's go to the bedroom. The boardroom, yeah.
Do I need an appointment?
You can register, yes. So that way we would know that you attended and you'll get a credit if you want it. Oh, I need a printout. Okay. Well, can you print out the attendance sheet? So I didn't print it. Okay, so it's 10 o'clock. You want to wait a little bit? Okay.
Sheet.
So what about you? Are you experienced user with SciNet?
I'm several.
Okay.
But I still want to.
Okay, excellent. That's why we're here. So if you guys have any questions during the presentation, just feel free to ask, because I have like general information here, but if you have more specific questions, please just ask. And Ramses is going to print the attendance sheet. So based on the registration, you can just sign your name saying that I'm a visitor here, and you get, I think, 1 point to our 1 credit for our certificates. Like, it's not necessary, but if you accumulate so many points, you can get a certificate from SciNet that you attended the courses, and maybe you will find you know, a use for it. So that's what we're going to do right now. That's why we want you to register. So we have your name, so it's easier for the system to then generate. Okay. Thank you.
Save on the table. That's it. Just write your name and an email. And you have a SciNet account yet? Yeah. Okay, if you know your username, do that at the end. Yeah. Just
Or you can say something there.
I can say something and it disappears.
Oh, okay.
Just to show it. We have to do snap live chat there.
We are on UFT time, 10:10. Okay. So let's start. Okay, so good morning, everyone who's here and remotely listening to us. So my name is Alexei, and together with me today is Ramses. We are HPC analysts at SciNet here at the University of Toronto. And for those of you who maybe started to use Niagara or just starting, this session hopefully will clarify some questions. Please feel free to ask any questions. We have a chat, I think, available online, so please post your questions and we will answer them. So we will briefly talk about what is SciNet. So after that, we mostly will be discussing our supercomputer, which is called Niagara. And we will also talking about some tips how to improve your performance and get the maximum out of your code. So SciNet is a consortium here at the University of Toronto. And what we really do is helping users, researchers, to be more effective. So if you have any question with regard to your code, something is not running, or it's running but slow and you expect something greater, or you would like to parallelize your code across multiple machines, please send us an email at support@SciNet, and we have a team of several people that will pick up the question and help you with it. So there are also other consortia available in Canada, namely SharkNet and WestGrid. They also are running big machines. So these machines are Cedar, Graham, and Beluga. But there is a little bit of a difference between them. So these machines are so-called general purpose. It means you can request literally a machine with 1 core, 2 cores. But when it comes to Niagara, it's so-called a large parallel cluster, meaning that when you request a resource, you get a full node. So for those of you who may be not familiar with the terminology, by the node, I mean like you're given a laptop. But this laptop has 40 cores. So this is a very powerful machine, and it's your responsibility to make sure it's running well. Because everybody gets some certain time on the machine. And if you are getting a whole node, for example, and you're just not doing anything, you're idling, you will be still accounted for like you used a full node for a whole period of time. And then it reduces your total time available on the machine. So obviously, we're interested in using the resources as well as possible. And we want to make sure that you are efficient with your work. So we're also available, we also have certain clouds in Canada, but this is a little bit different story. It's something if you need to maybe host a database or a website, then you can go to the cloud systems. Today we will be talking about our Niagara system. Just be aware that if you need something else, there are also systems available. Once you get an account with Compute Canada, which you guys probably have, you get access to all of the systems. So you can actually go and perform your analysis, your research on any of these machines. So this is Niagara. This is our system. So it's literally a big machine. So if you've never seen a cluster, you can think of it as a stack of laptops. So you have many laptops stacked one on top of another and put in like a closet. And that's what we have, we call it a rack. And you have nodes inside of the rack. And then we have many racks stacked together. So this is a highly parallel cluster. We have Niagara. We also have several other clusters. We have P8 cluster which has GPUs, but it's only, I think, 4 nodes. So it's not very large, but it lets you play with GPUs a little bit. We have also SOSIP cluster for those who are users of SOSIP. And what is interesting, we have a teach cluster. And this teach cluster is used by some groups to teach parallel computing. So let's say professor wants to teach a highly parallel optimization algorithm or something to do with massive parallelism. They ask us to get access to the teach cluster, and they can use it for the whole term. So I think we found it quite helpful because students get actually a sense of working in a large machine like that, which usually don't get access to. And we have additional long-term storage, which is called HPSS, and we will be talking about it a little later on. So on top of running the machines and providing support to the users, we also provide extensive training. We found out that it's better to educate our users how to use the machine, how to be more efficient. And we have a lot of demand for this kind of training. If you notice here, some classes are listed, and we're constantly improving and we're listening to what users want. So if they want another language, we're going to introduce it. For example, last summer school, one of my colleagues taught Julia, for example, because there is a increased demand for Julia. But on top of that, as you can see, different courses, including C, C++, and maybe data science, neural networks are very popular. I need to notice that Niagara doesn't have GPUs. So for machine learning, you usually need GPUs. You can use CPUs, but there is a big advance in using graphical processors. However, yep.
So
Yes, but you need to be a SOSIP user. It's for users who are connected with the industry. However, first of all, right now you can go to other systems like Cedar and Graham, and you will have access to GPUs. And very soon, I would imagine starting next year, we do open access to our GPUs. We just got additional GPU cluster, so it will be available to our users, and everybody will be able to play with it, and you don't need rack allocation for that. So if you're interested in attending our training sessions, you get credits. We found out that people want to have a record that they attended these training sessions. So after attending so many of them, you accumulate a certain amount of points, and you get a certificate from us that yes, you finished, let's say, a data stream training, data science training, and you get a certificate. So you can present maybe to place of your employment or anywhere you would like to show your knowledge. So as I mentioned before, Ramses and Alexei were here, but we also have other people working full-time. And as you can see, we have quite an extensive number of people with a lot of experience. So please send us an email at support@SciNet. The email is right there on the bottom. And somebody will help you. Questions like MPI, Python, R, GPU also. So please feel free to contact us. Again, if you feel like you maybe need a little bit more knowledge, just attend our seminars, our classes, and you should improve your knowledge after that. We work very heavily with people after classes to answer their questions. Very often people come with just particular questions about their research, and we're trying to help as much as we can. So just remember, you can contact us anytime, and you'll get help. Now, let's talk about Niagara. So currently we have over 60,000 cores available, and we are extending Niagara by, I think, 20,000 more. So we will be having a system with over 80,000 cores very soon. Currently, I think it's 76th system in the world from our perspective. When we just deployed it, it was number 59. But as you can see, a year from the time we deployed it, it already went down several positions because constantly new clusters are being deployed around the world. It's a very popular area of research nowadays. So, as I mentioned before, every node has 40 cores, and you get access to all 40 cores at the same time. There are quite big nodes. They have almost 190 gigabytes of RAM, and they're all running, of course, Linux. So if you're not familiar with Linux, the way you access the supercomputer, you use your terminal via SSH. We will be talking about it later on. But remember, no Windows. So if you use Windows, you would need to download a particular tool to connect to Niagara. There is no graphical user interface when you connect to the system. So one more thing to notice is that our file system is slightly different than that you have on your computer. Because if one user is writing something and the same user might have another program reading something, you want to make sure that everything is consistent. So we employ a so-called GPFS system. It's a parallel system which is very, very fast. However, it requires certain handling of it. Namely, it doesn't like a lot of small files. So be aware that writing a lot of small files on the file system will slow down your performance. And this would be a tip. We will be talking about it more close to the end of the class. So if you don't have an account, you have to get one. And this is kind of a two-stage process with Niagara. So first you need to apply for Compute Canada account. If your PI, your principal investigator, has an account, he would just need to approve it. So you will apply under your PI. If your PI doesn't have an account, then he or she should get it first, and then you can apply under the PI. And after that, after you've been approved, it will take a day or so, you can apply for the account on Niagara. Just follow the links, and you'll get it very easily. Everything is free. You don't have to pay for anything. So after that, you will get access to Niagara system. After you get access to the Compute Canada, the first link, you get access to all other systems. So you can perform your research on Graham or Cedar or Beluga. Beluga is also a recent system that was deployed in Quebec. So this is how you access the supercomputer. So once you get your username and a password, you need to get a terminal. So if you're using Mac or Linux, you already have a terminal. If you're using Windows, then you need to download PuTTY, for example, or Mobile Xterm or Git Bash, or find another client that can perform this kind of connection to the remote server. Yes? I found Mobile Xterm being very nice, and Git Bash. So these are two that we usually recommend. Git Bash. Let me see. Maybe I have it mentioned here. Well, it's Git-Bash. What is the benefit of having Mobile Xterm? It comes with the X11 server, which means that you can actually connect to Niagara and then display some graphical user interface, and it will be transferred back to your computer. With Git Bash, if you're working, for example, on Mac, if you're working on Windows, you would need to install additional software, I believe. So if you don't need graphical user interface, Git Bash is fine. So that's what we usually recommend. And after you get the terminal, you connect to Niagara just by using this command, SSH, and then your username at Niagara at computecanada.ca or niagara.scinet.utoronto.ca. Notice this flag -y. So -y needs to be added if you're going to perform some analysis that will show you a graphical user interface. So when you log into the system, you don't get a mouse or anything to interact with, only a terminal, only typing commands. However, you can type a certain command and it will display a graphical user interface for you. For example, visualizing your plot. And if you specify -y flag, it will take this plot and it will actually display it on your system. So it will kind of download it over the internet. Again, if you don't need any graphical visualization, you don't really need the flag, but you can just have it there. Yeah. So Mobile Xterm and Git Bash, if you download it, you can see there it's Mobile Xterm. It's a second line on Windows, it says. So this is one of the examples. It is graphical interface on your machine, but you're typing commands inside of this terminal. And these commands, once you connect to the server, will be executed on the remote machine. So it will be executed on Niagara. you need to, for Windows, you need to download a separate tool, and then it will work. So you can make it work, but MobiXterm comes with it already. So it's very convenient. So because it's a shared system, it means many of you as users are working on the system. You're talking about thousands of people running codes. How would you make it efficient so everybody gets their own part of the system? Well, the way it's usually scheduled on large supercomputers is through the batch jobs, meaning that you run your code on your machine. You verify that everything works. Then you make sure that the code works on the supercomputer. We have so-called login nodes. So once you type SSH and you access our system, you are dropped on the login node. We have 6 login nodes, and you will just randomly assign one of them. You can jump between them. And on this login node, you can do pretty much any short test. You can just make sure that your code compiles. You can build your code. You can maybe run like a minute or two to see if your code actually is running well. But you're not supposed to run the whole calculation on a login node, simply because this login node is shared between all of you. So all of us go there, and if somebody starts running a job at 40 cores, full capacity, it slows down everyone. I cannot compile my software. So if I'm compiling a software for someone, for example, and the other person is running a big calculation, it really slows down my work. So we would write to the user, so please stop your calculation. So how do you perform the calculation? You put all your commands in a script. It's a bash script. And we have examples on our wiki page of simple examples of scripts. You simply arrange everything in the proper format, and then you submit to our scheduler. And the scheduler will look at all the available accounts and all the available jobs, and it will find a slot for it. And your script will run eventually. You get maximum 24 hours of wall time, so basically 24 hours available for you to run the job. So you have to fit in this 24 hours. If you don't, the job will be just terminated at 24 hours. So as you can see, everybody gets up to 24 hours, and you can request as many nodes as you want. So you can get as many computers. They're all, of course, interconnected, so you can run a parallel job. And these jobs are run on the compute partition of our system. So our system is divided into, I would say you can think of it like 3 partitions. So you have login nodes where you just run your maybe compilation or just as a short test. Once you verify that your code is running, you have a debug partition, where I will be talking about requesting it later. This is a partition where you get the full node. You can get 2 or I think 4 nodes as well. And nobody else shares it with you. It's totally yours. But you also can do whatever you want with it. You're not responsible to make it particularly heavy used. You can log in and you can play with your code there. It's not shared between anyone, only yours. And after that, once you figure out that your code does scale well, you submit a script to our compute partition. And please be aware that compute partition does not have access to the internet. So whatever you accessing from online, you have to download first, save it on the storage system, and then access it from there. So login nodes do have access to the internet, but not compute nodes. Just be aware of that. So we have convenient links to shortcuts to access several file systems. And as you probably have partitions on your hard drive as well, you have like let's say disk C, you have maybe data, you have maybe program files. We have also divided our space into home. So this is where your files are stored. This is usually used to maybe install something and you constantly accessing it. You have Scratch system, which is constantly purged. It means that if you write something to the system and you're not accessing it for 2 months, it will be wiped out. If it seems weird, you have to know that home is only 100 gigabytes. Only, well, maybe it's enough for you, but Scratch is 25 terabytes. So you get 25 terabytes, and people sometimes fill it in quite fast. Your program can write a lot of output, and you have to go through the output and select what you want to keep and what you want to just discard. If you go through your files and you saved something, you can leave the rest, and in 2 months it will be just deleted. So as you can see, you get a large storage, but it's also not permanent. It's constantly being wiped. You will get an email saying that, you know, these are files that's going to be removed at a particular date. So you usually get a heads up, but just be aware that these files will be removed and there is no backup.
Who's the files?
In Scratch system, it will be deleted. In Home, no. Home is permanent. Whatever you put in Home is yours and it's backed up. It means, so it's about 100 gigabytes. 100 gigabytes, yes. Yes. If you feel it's not really enough, you can apply for rack allocation. Can you get Home there? Project. Okay. So there's on top of these two files spaces, we have also a project space, which you don't get if you don't get rack allocation. So your PI once a year can apply for an allocation saying that what Niagara offers by default is not enough. I want more resources. I really need like a large computation, and maybe instead of using one node for a while, I need 1,000 nodes. So in this situation, PI will apply for allocation. He or she would need to create a proposal saying, okay, that's what I'm doing. That's why I need so much power. And there is a committee that's going to review it and decide whether it's a legitimate request or maybe it's a little bit too much. And after PI gets the allocation, PI can request also in the allocation the project space. And here you can get quite a lot of space. But the project is slightly different from Home from the angle that it is backed up. But since it's such a large storage, it's not intended to be used like Home or Scratch. Meaning that if you put something there, you should intend on keeping it there because it's backed up. And if you start moving files around, it's simply our system has to keep up with that. So it puts a lot of stress on our system to back it up because we do want to back up your files in case you need to restore something. So just be aware that whatever you put on project, just try to keep it there. And it's usually when, let's say, you perform some calculation, you created some data, and now you need this data for the next calculation. You can put it on storage, and it will be just accessed in your new calculation from storage. That's totally fine. It's usually a big one, so just keep it there. Home will not be enough, but storage you can get quite large. So here on the slides, you can see that you can access Home and Scratch using these links. Project also is available with a $ project variable. And additional, we have a burst buffer space. And we notice that some people write a lot of small files. And as I mentioned before, if you start writing a lot of small files on the system, it really slows down the performance of actually everyone because it's a shared system. So we usually encourage people in this situation to tarball it. Basically, if you have to write a million small files, save it, for example, in the memory or assemble it together in one big file and then write one big file on the file system. In this situation, you don't get any penalties for using that. But if you start writing a million files, you will really slow down your own performance. So you will be thinking that your code is slow, but in fact, it's just because you're writing so much. This is the slowest point in your code because the computation is fast, but writing anything on the disk is actually slow. So some codes could be assembled, especially if it's custom made. You wrote the code, you can work a little bit with it and get a better performance of writing to the storage. However, if code is not yours and you don't really have a capacity of tinkering with it, we can give you a burst buffer space. And this is an SSD space. So if you're familiar, SSD is like a flash drive memory, which is totally fine with a lot of small files written to it. It is smaller, significantly smaller than the space that's available as a regular GPFS system. However, it's there. And if you email us saying, I need this particular space, my program will really benefit from this system, we can give it to you. But first, we will encourage you to look through your code and make sure that you actually cannot convert these millions of little files into a large big file. So these are the spaces available. On top of that, we have archive. So archive space it's an IBM HPSS system. And what it does is, let's say you perform some calculation. You wrote 25 terabytes on Scratch. And you suddenly have another project going on. And what are you going to do with this data? Well, you maybe use the whole month of resources to generate it. So you want to preserve it, but you don't really need it right now. So the good thing is to put it on archive. It's a tape space. And when I say tape, it's literally like an audio cassette. Basically, it's a very old way of storing it. And it's very slow, but it's huge. We have a lot of space available, and we're constantly expanding it. And if you have results that you're not going to touch for a couple of months, yes, it will take a while maybe to put it there. But it's saved. So now you can clean your Scratch after that and continue with your other research. So there are some also requirements about archive. You get it by default. However, you should, again, tarball your outputs in a larger files. Archive doesn't like a lot of small files. So just be aware when you work on large supercomputers, try to avoid many small files as much as you can. Especially if you have some logs files or anything. Maybe you don't even need them. But if you do need small outputs, combine it into one big one. That will improve your performance on the supercomputer tremendously. And it's relevant not just for a Niagara system, it's also relevant for pretty much any supercomputer. Because you're talking about shared system between everyone. And if you start hammering the system with your small input, small outputs, it will really slow down everyone. So we kind of mentioned the fast storage, which is a parallel file system. Archive is a slow storage, so it means it has slow write and read access. But on top of that, there is a RAM disk available. This is the fastest storage you can access, but it's temporary. So RAM disk is basically the space that's available on the node as a memory. It's a RAM memory, random access memory. And if you know that your code using just a little bit of RAM and you have a lot of RAM available, you can use this as a storage. Extremely fast, the fastest out of all of them. But you have to remember to save it at the end of your script, at the end of the job. Save it to a permanent storage, like project or maybe Scratch. Does that make sense? So it's very fast. It's a good idea to write there and then take it from there. Let's say you will write lots of small files because it's RAM. You're not touching the file system. So you write in lots of small files, let's say in RAM, then you just combine it into one archive, tarball, and you just save this one big file on the storage system. So it's a tip. So these are the quotas that you're given by default. As you can see, Scratch is huge, and Home is just 100 gigabytes, but it's usually enough to install some software that you're accessing once in a while. So for those of you who work with Python, do not install Anaconda. Please, do not install your own distribution of Anaconda. We have Anaconda for you provided. If you really need something, a newer version or anything, just write to us. We'll find a way. There is a interesting situation with Anaconda. For those of you who are familiar with it, it creates millions of files. And as I mentioned, system doesn't like millions of small files, and that's exactly what Anaconda does. So there are ways around it. If you really need something special, just email us. But by default, we have Anaconda installed. You don't see it when you log in, but I will tell just in a short while how to access all the software that's installed. We have lots of software installed on the system. So what is not mentioned here is that Home has limitation of number of files. So you have 100 gigabytes. And it might be a lot for you, it might be not, but you also have 250,000 files maximum you can create in your home. And it seems a lot. But you create one Anaconda environment, empty one. You have just barely, you have Python installed, and it's 50,000 files. So very often, people write into us saying, well, I only use 20 gigabytes out of my 100 gigabytes. Why it says that I don't have a disk space to write? Because that's what the system gives. Once you reach the quota on the file amount, it gives an error saying you don't have space. So people question, why is that? Well, when we look at their files, we can see that they have 5 Anaconda, let's say, environments, which take up the whole space. It's absolutely not efficient, simply because there is the same files 5 times. So on our wiki page, you can find more on how to use different virtual environments that does not pollute that much of your own system. Yeah?
Is there to say?
Yes. So if you're on a system, you can type disk usage. So disk, and then, so it's a one word, but U is capitalized. So it's disk, capital U, and then you have Sage. And it will give you the current disk space that you have, how much you use, how much in total you have, all your project archive, and how many files you have. It has everything there, and it's updated like 4 times a day. So clearly it's not like real time. So if you just cleaned up the whole Scratch, it still will show maybe for a couple of hours. It's every 3 hours, I think it starts. Like at 9, 12, and 3, and maybe later. But anyway, it's a good way to monitor how many files you have. So if you suddenly see that your disk quota exceeded, type disk usage, and you just pay attention to the number of files. On Scratch, you have 6 million files, so you have lots available there. But still, it doesn't mean that you should install Anaconda, simply because it will really eat up your quota. Okay, so as I mentioned before, home is backed up. It means whatever you create in your home would be backed up, and if you suddenly delete it accidentally, just email us and we will restore it for you. Scratch is not backed up whatsoever. So whatever you write to Scratch and you deleted it, it's gone. We're not joking. It's not backed up. So just be aware. When you work on Linux machine, once you type RM for removing anything, there is no trash bin. You can't restore. It's gone. So just be aware of it. Once you remove something, it's gone. Even if you move something, and let's say you will overwrite the file, it's gone. If you do this on home, you have a way back because it's backed up. The same with project. Project is backed up, but it's much larger than home. It's by location, so depending how many terabytes PI asked, it's quite big. So notice also that home has, that login nodes have access to the internet, but compute nodes don't. So be aware of that. you have to store things first, and maybe putting something on the project and then accessing it from the compute node to the storage makes sense. Okay, so one very important thing that people, especially those who just started to use the system, are confused with, once you submit the job, it cannot write to home. This is very important. So once you log into the system, you can do whatever you want with your home. You can create files, remove files. But once you submit your job script and it's running on a compute node, you cannot write to home. It means you cannot delete the file from home. You cannot create a file on home. You can only operate with Scratch and project, and burst buffer, of course. So why is it done? Well, simply, you probably are going to generate a lot of data. And home system is backed up. It's only 100 gigabytes. It might not be enough. So just work with Scratch, write everything to Scratch, select what you want to keep, and then you purge the rest, or you put, let's say, whatever you saved to project. Or if you want to keep it at home, if you don't have project allocation, that's fine. So be aware of that you have to submit also your job script from the Scratch, because your job script can create a log file. And by default, it will create a log file in the same directory where it has been submitted. And since the home is protected, it's read-only, it might give you an error that's saying, I can't write to home. So just be aware, copy everything on Scratch and launch your job from Scratch. Okay? So home is basically intended for some software installation. Let's say we don't have a software that you really want. This is a particular software for your group. It's a good point maybe to install it in project or at Scratch, or in home, and just access it from there. So you can read, but you cannot write. You're not going to modify your software once your job is running, but you will just use it. Okay, so how do you move data? Once you log in, you are on login node, and you can transfer small amounts. If you need to upload something, you need to download. So up to 10 gigabytes is all right. You can transfer between, let's say, your computer and login nodes. But once it's become too large, on login nodes, we have a limitation of how long you can run a job. Actually, how long you can run a process. And if it's, let's say, over 10 gigabytes, it will just take a while. So your download or upload will be just terminated because it's too long. So we have special dedicated 2 nodes. It's called data mover nodes that are just created for that purpose, to download and upload large quantities of files, large data sets. So you go there, you access them. You have the links here. It's Niagara Data Mover 1 and 2. You can access them from the login node, or you can log in directly into them. And then you just do your SCP, rsync, whatever you want. And you don't have a limitation there on how long you can run your downloading or uploading process. If you find yourself in a situation where you have to constantly upload, re-upload, so you use a lot of these data movers, we have a Globus system available. That's a convenient system that uses web interface. So you can actually go to the website and connect 2 endpoints. Let's say you want to connect your laptop or your lab machine with Niagara, or you can connect, for example, Cedar, another supercomputer, with Niagara. Globus provides many endpoints to different systems in the world, in fact. So if you need something from Zurich, you can just go and download it from there. And then you submit a job in Globus system saying, I need to transfer this folder into my folder. It's just literally like drag and drop. And it will be finished at some point. So clearly, if you're transferring 25 terabytes of data, you're not going to look and sit in front of a computer and watch how 25 terabytes are transferring. You just leave it in the queue, and it will be eventually transferred. It will come back maybe in a couple of days, and it's finished. So this is very convenient, but if you just have a couple of simple files you want to transfer, just feel free to use data movers for that. And on top of that, as I mentioned, the tape storage, the one that's slow but large, massive, you can use to transfer between your login nodes and the tape drives. So it's kind of a separate storage, so you need to transfer between them. If you find yourself in a situation where you need to use it, go to our wiki page. The slides have a link. It's docs at SciNet, docs.scinet.ca, and you will have example scripts which you just need to copy paste. Make sure that everything is according to your desire there, and that's how you can transfer files between login nodes from your file system, your home, and archive space. Questions? Good. So we have a lot of software installed, but we often get an email saying, well, I logged in and there's not even a compiler, nothing is there. How would I run anything? Well, there is a reason for that. Simply because when you have many thousands of people accessing the same system, each of you guys need a different version of maybe the same software. And that conflicts. Two versions of the same software might just not possible to have loaded at the same time. So what supercomputers usually do is that they provide you a module system, meaning everything is installed, it's in the system, but you need to run a command to load it, so you can actually run anything. And this is available through the module commands. If you type, for example, module spider once you're on Niagara, it will give you all the software installed right now. And you will see that the list is quite long. This is an example. So if you type module spider, for example, you get all the software installed with description. There is no description here, but the list is quite long. And we actually have more software installed since that particular snapshot was taken. And module as a command has different subcommands. So for example, if you selected the software you want to load, module load and then the module name will give you access to this software. So if you need a compiler, let's say GCC, module load GCC, and you will get access to GCC. Now if you type GCC, it will say, well, no files, specify the file. So it's there available. Now, if you want to remove all the modules, you want to have a clean environment, nothing's loaded, module purge will do this for you. If you type module spider, it will give you everything available on the system. And if you want to find particular information about a certain module, you just type module spider and this particular module with the version. So because software comes with versions, we have the same software installed with different versions. For example, if I go back, as you can see, Anaconda 3, for example, it says Anaconda 3 510, and then comma, you have other versions installed. So the same software has different versions. And simply because some of you maybe need an older version because your code will just not work with a newer one. They introduce some break and change in it. So it's good to have some sort of different versions, like for example, CMake 3.10.2 or 3.10.3. Some software just need a particular version because they hard-coded in a CMake file. So be aware of that we have multiple versions. So module list is also an important command that will give you everything that's loaded right now. So if you type module load, let's say GCC, module load CMake, module load something else, like on the 3, and you will type module list, it will show you what you loaded. So it's good to know, especially if you, let's say, work with us, we might ask you, can you send us back what you have loaded? Because then we can know maybe you have a conflict between the software, or maybe you haven't loaded something. And if you run module spider, you will see actually the first two modules available are called NIANV and CCN. And Niagara supports two software stack. Software stack, you can think of it as a combination of different software installed. So when originally system was deployed, we had a very advanced processors that supported newest instructions for the processors, and other system in Compute Canada, they had an older hardware. So we wanted to take advantage of having the newest processors. So we started to build our own software, because the software that was provided by Compute Canada was a little bit wasn't supporting the latest instructions. It wasn't outdated because it was supporting like the latest packages, like latest software, but the software wasn't compiled with the flags that we could actually use on our system to give better performance. So we started to create our own stack, and we put it as a Niagara environment stack. So this is what you get by default when you log in into the system. But if you find yourself that you really need software from a CC stack, Compute Canada stack, for example, you come from Graham or Cedar and you ran it there, and you're really accustomed to a particular package that's there, you will get the same thing when you log into Niagara. It's shared between all the systems, and you have access to it. It's just slightly different. In order to access this software in Compute Canada stack, you need to run the command. So module load cc-env, then you have architecture. This is the new commands that I mentioned. It's AVX 512 that Niagara CPUs support. And then you need to also load std-env, so standard environment. That will load. So basically, after this command, you will have exactly what you have when you log into Graham or Cedar. So it's convenient. You get exactly the same anywhere you go. Just remember that on Graham and Cedar, you can request as many processors as you want. Here you get a whole node. So this is still holds true. So we find our users sometimes using the same software all the time. So they find, well, why I have to log into the system and type, for example, module load GCC every time, or module load Anaconda. So I will put it in my bashrc. So bashrc is a file that is being read and executed every time you basically log in to the system. So it's convenient. It's like putting our load when you log into the system. However, it's very common that people work on one project, and for half a year they worked on one project, they put some software, and they forgot actually that they load in module something. And now their PI is saying, well, no, you have another project, you're working on something else. And they're loading the module, and there is a problem now, simply because they forgot that they're loading other software in their bashrc. And they write to us saying, well, this doesn't work. The first thing we do, we check their bashrc. You remove the module load command from bashrc, and everything works after that. So we advise you not to put anything in your bashrc from the module load standpoint. So if you need to load something, load in manually, or create a script. So that's what commonly we see is that, for example, you have a software that has a lot of prerequisites. You have to load many other packages before you can access, for example, your target module. People just create a separate script, and they just run script once, and it loads everything for them. It's a good idea because then you can just take the same module load commands, a bunch of them, let's say 5 module load commands, and just copy paste it into the job script. Because when you run the job script, it will ignore your bashrc. So if you're loading something in your bashrc and you forgot about it, you submit a job, and you're not loading it there explicitly, it will not find it. It will not find the software. So you have to be loading everything manually, especially in the script file. Okay. So another thing to notice is that we are updating software once in a while. Well, when we have a new version coming, which is stable, and you can, well, let's say, launch software by, you can load a module by just running module load, let's say GCC, and GCC comes in different versions, and you get a default version, and default version is technically specified by us, and if you used to have a default version, let's say 7.3, and we update it to, let's say, 9.3, your software might not compile with this version. So it is better to put versions directly in your module load commands. So instead of saying module load GCC, type module load GCC slash, let's say 7.3.0. This way you guarantee that every time your job runs, for example, you always have the same software. Because if we update it, you'll get a newer one, and it might break something in your code. So just to be more specific, explicit, use versions. Doesn't cost much, but you will be sure that you get the same thing over and over again. Once its version is installed, we usually don't touch it. So it's there available. However, if you find out that something doesn't work, please email us, and maybe you would need some flag, because when we install software, we know nothing about the software. People sometimes write to us saying, well, I have this DNA chain, and then they introduce all these theories. I think none of us are experts in DNA. We might know something, but some of us are astrophysicists, mathematicians, and you shouldn't expect from us that we really know what you want us to install. So if you know that this software has to be installed with certain flags, for example, tell us and we will just install it the way you want it. Okay? Just be aware that we will help you with the software part. We saw enough times different problems, so we know how to solve it. But we can look into your problem, but we would be very grateful if you tell us what you want from us to see. Okay, like particular version, for example, or certain flags for compilation. Okay, so here is an example how to load, for example, OpenMPI. If you can see that, as I mentioned before, modules sometimes depend on one another. So you trying to load a module and say, what does it say here? That you can't load it. You can just type module spider and then the module name. It will give you more information. For example, you have different versions. And if I go to the next one, let's say you decided you want to go over a specific version. It will tell you that you also need to preload compilers. So certain software depends on particular headers or include files. So you have to preload compilers. And on our system, we have a choice of two compilers. You have GCC, which is an open source compiler available widely for many platforms. That's most likely what you're using on your Linux system. However, we also provide proprietary Intel compilers. Since we're running Intel hardware, we have access to Intel compilers, which are, they tend to be slightly faster. The code that you compile with Intel compilers might perform better than with GCC. However, it also might be unstable. It really depends on the software. We found that some software is really stable with GCC, but may be less stable with Intel. But it also can run much faster. It really depends on the software and how it's been, the code was written. I just want you to be aware that Intel compilers are available. You don't have to pay anything for it, so why not give it a try? You have slightly optimized, sometimes even a lot of optimizations are done from the Intel part to make codes more efficient. Okay. So as you can see here, if I choose to use OpenMPI with Intel compiler, I just have to preload first Intel and the particular version, and then I will load OpenMPI libraries. Many times we have, questions. How would I run MATLAB or some other commercial software? Well, we do not provide licenses. So except proprietary software that will benefit everyone, like compilers, or for example, certain debuggers, we have licenses. But MATLAB is not one of the software that we can buy a license for everyone. So you have to come with your own license. If you have your own license, we can help you with MATLAB. If you have questions particular about MATLAB, you can go to our wiki page, and it has in details steps what you can do to make your code run. With MATLAB particularly, you can compile your code into executable and you can run it on our system. I think you don't need a license for that. So, but once it's compiled, it can run. But you need the license to compile on your own machine. So, what we sometimes offer users is to use the open source alternative. Like you have Octave for MATLAB, you have Python R. And this is usually what the whole world is moving. Let's say if you do machine learning and we have some code in MATLAB, we usually recommend just write it in Python because the whole world is using Python for machine learning. Just rewrite it. You're probably going to do this eventually anyway. So we are all for open source alternatives. However, if you must perform something with the commercial software, bring your own license. If you go to other systems, Cedar or Graham, they provide some licenses. So, but you have to figure out it with them. I think they have MATLAB licenses for some users, or even for everyone actually. Again, so if you have your own license and you maybe provide us with the detail how to install something, if it's something complex, we will be happy to help you. Okay, as long as you have your own license, it will be only your software. Nobody else will access it. We have ways to handle it. Just tell us what you want and we'll help you. So this is an example of how you can, let's say, compile a code on the system. So let's say you work on Windows and you work on Mac, or let's say your Linux is not the same that we're running. Chances are you need to recompile your code. We run CentOS on the system. It's just better to recompile your code on the system directly. So that's what you need login nodes for. You log in, and then you can just directly compile right there. You get a binary executable that you will run in your job script. And how you do that? Well, for example, your code requires GSL and Intel compilers. Okay, you can use just GCC, you can use Intel. Let's say here we have some code. This is a C code, and we will use Intel compilers. This is an example of how to compile a well-optimized code. So you would use optimization flags like -03, 02 minimum. Xhost in this situation is optimization that will turn on all the flags for a particular CPU. So it will figure out that, okay, this is an AVX 512, so it's the latest, let's say, processor. We will turn the latest instructions. So you will benefit from vectorization of your code, for example. Again, you don't have to think of it very much if you're not familiar with that. Just use, let's say, -03 Xhost with Intel compilers. If you're working with GCC, use -march equals to native. In fact, this command will work with Intel compilers as well. So it's a good idea just to use -march equals native when you compile your code regardless. It will work. So remember to specify optimization flags. Otherwise, you will get a much slower code, significantly slow. Like if you've never tried comparing optimized code with non-optimized code, you should to see. You will be stunned by the difference. And I'm not even talking about parallelization yet. It's just a serial code. And again, then you can link your libraries. And Intel comes with its own MKL library, math kernel library, which has a lot of algebraic function already in it. Like if you work with BLAS, for example, let's say you have matrix multiplication, you don't need to write it your own because it was written many times by many people who optimized it, and they introduced some tricks to make it even faster, parallel. So you can either use, let's say, BLAS libraries, or you can use MKL. We recommend to use MKL because it's a highly optimized library from Intel, and it's available. You can actually download it on your computer. You don't need a license for that because Intel compilers are proprietary, but the libraries, MKL, is available, I think, for free for anyone. So you can use it on your computer as well. So this part I kind of already mentioned before is that once you log into the supercomputer, you have login node, and you're not intended on running your jobs there. What you need to do is you need to compile. If your compilation takes over an hour, for example, some software is really, really heavy. It really takes a lot of time to even assemble. You might want to request a debug node. So the way you do that, you just type debug job and then how many nodes you want. Let's say you want to just compile something, debug job 1, debug job space 1 will give you one node for 45 minutes, I think, or an hour, something like an hour, I think. It's completely yours. You can compile. You can use all 40 cores. it's totally up to you. So this is a good place to test your, let's say, parallelization, how well, for example, your OpenMP code performs. So you can see whether you're loading all 40 cores. Because when you're given a compute node with 40 cores, you want to make sure you use all of them. You're not using 20 out of it. Again, it might depend on your memory, because some jobs, they don't use a lot of CPUs, but they use a lot of memory. And then it's a different type. So you want to make sure that you're using, for example, all 180 gigs available or 170 gigabytes. So if you, for example, testing MPI job, let's say it's a job, or let's say you have a cluster, R cluster, you perform some calculation on multiple nodes. Let's start with 2 nodes. So it's a good place to start. Then you will request 2 nodes, debug job 2. It will give you 2 nodes for 45 minutes, I think. And here you can make sure that your code actually is running on both nodes. So you can directly connect to them, and you can verify it using top, htop, just to see that it's completely loaded. Remember that you can, on the compute node, you also can load. You can also log in to every single node manually. So let's say when you submit a job, it says that Niagara 0001 is the node that your job is running. You will be allocated, given a particular node that is available currently, from like 0 to 1500. And you can log in directly to it, and you can monitor the job performance. You're allowed to do that. You can do this on a debug job or on a compute partition. So if you checked, let's say, your 2 nodes, you can request debug, let's say, job 4. I think it's the maximum you can get. 4 nodes, you get like 15 minutes. So you can run your script again to see whether it's scaling well to 4 nodes. So if you're planning on running a massive parallel job, for example, 1,000 nodes, just use a little bit more time, maybe 15 minutes more, to test that you can actually scale from 2 to 4 nodes. So it's very important to perform this little scaling test to make sure you do get this scaling across multiple nodes. It's very important, because sometimes we see that a person checked on 1 node, and then they changed, for example, node from 1 to 10, but they didn't change another parameter in the script, and they launched the job, and they waited for 24 hours, and then they discovered that 1 node was running, and 9 nodes were just completely idle. They didn't do anything. So make sure your code is running well on multiple nodes. I mentioned before that you submit a job. That's how you do that. There's a command as batch, and then your script. So now we will be talking about what do you put in this script. I mentioned already this part. So hyper-threading. Well, before we talk about job scripts, maybe you're aware that your computer might have 2 cores, but it actually displays as 4. So you have physical 2 cores, but technically like 4 logical. It's basically system is running 2 threads on each core. So you don't get a benefit of really doubling your number of cores, but you get some sort of performance boost. So it means that we have 40 real cores. It means we have technically 80 logical cores. And well, it doesn't cost you anything to try running it on 80 cores. So if you do get a significant benefit of running 40 versus 80, go ahead and run it. But if it's not enough, you don't really need to use all 80 logical cores. As you can see here, from what we saw, the speed up from going from 40 to 80 is not that great. It's not like you're really doubling your performance. It also depends on the code, how well it scales. So give it a try, and maybe you will really benefit from using all 80 logical cores. So here, here's an example of an OpenMP job. So this is a script that you can just take, replace your, let's say here the executable is right here. You can just replace it with yours and run it. Yeah?
The cores that.
Yes. So this is how many CPUs on the node are available. So in fact, when you run your OpenMP program, you have control of how many threads of team of threads. Well, you have a team of threads and how many threads you want to have in the team. So maybe in your situation you just need 3, and they're very like memory extensive, or maybe you want to take them all. 40 threads is fine with you. So here you can specify how many threads per task. Yes. It's like saying that OMP num threads equals to 40. As you can see, so you have module load Intel, and then you have OpenMP num threads. That's how you control how many threads.
Is there any difference if I have one node with and 2 nodes with the
So when you talk about OpenMP code, it's a shared memory parallelization. It means that it doesn't run across the nodes. So you have OpenMPI, and this is an MPI protocol where you can run your code across multiple computers. What OpenMP is about using all the cores available on your current machine. So it doesn't make sense to request, let's say, 2 nodes if you're going to run OpenMP code, because it will just use 1 machine. It does not jump on the second one. Does it make sense? So when it comes to OpenMP, it's about using full resources on 1 machine, on 1 computer. So if you're talking about a machine with 40 cores, you definitely want to use these resources available. So you would run 40 threads, or maybe even 80 if you want to use hybrid thread. Does it make sense? So this is for a job that runs just on 1 node, but you want to use 40 cores. Sometimes that's all you need, because your laptop might have 4 cores. Maybe if you're advanced enough, maybe it has 12 or 16 cores. But it's far from 40 that enterprise grade hardware provides currently. So the way the script is structured is, you can see that the first line is called the shebang. You have to put it in your script anyway. But after that, you have sbatch commands, and if you see, there are comments. So actually, this script will run without the scheduler, because there are comments, it will be just ignored. But for the scheduler, these are actually parameters that it's going to read. So, and the way it will run the job is it will allocate you 1 node, so 1 full machine, 40 cores, for 1 hour, so time here, it's a wall time. And then you have a job name. For example, if you want to have a particular name, which you probably should, to differentiate what you're calculating, give it a meaningful name. You can specify the output and whether you want to get, let's say, email when the job finishes. So after that, remember to load all your software that you need, because without loading, nothing will be visible. And then you can set, for example, your parameters, and then you run. Basically, the last command is to run your code. And then you will submit it is you type sbatch and your job script, and you're good to go. You submit it and you wait. You can just go do other stuff, and you come back, and maybe in an hour or 2 hours, it's finished. Like, you don't really need to sit and watch when it's going to run. So here is the description of what is happening. You guys all have slides, right? So you can come back and reread it, because what it's on the right side, I just verbally announced before I showed it to you. So here is an example of MPI code. And here, as you notice, we have 2 nodes. And this means that the code will work across multiple machines. Here we have slightly different commands. So for example, instead of CPU per task, we're using n tasks per node. And please use this, n tasks per node, instead of n tasks. We see very often that people use n tasks, and n tasks means how many MPI processes I want to run across all nodes. Where n tasks per node says how many MPI tasks I would like to run per node. Why is it important? Well, very often we see that people tested on 2 nodes and now they want to say 10 nodes. And they use n tasks. And let's say n tasks on 2 nodes would be 2 times 40, 80. So they specified n tasks 80. And now they change in nodes from 2 to 10, but they didn't change n tasks. Because you're supposed to adjust n tasks proportionally to the number of nodes. But they didn't. So what they have now, 10 nodes running for 24 hours, but only 2 actually are working. 8 nodes are idling. That's not what you want, because it's a whole, it's not the purpose of a calculation. So if you specify n tasks per node, it will automatically scale it for you. So now you just change the number of nodes, and it will automatically adjust the number of MPI tasks for, it will just make it 40 on each node. So just be aware, use this one. And again, the way you run it, similar, you need to load the compiler, you need to load particular MPI module that you want to use. You want to use Intel MPI, you want to use OpenMPI, and then you just do MPI run in your program. Again, as batch to use as batch to load your, to submit your script to the scheduler. So the way you can monitor your job is a very important command at sq. So you put sq, and without any parameters, it will give you all the queue available. So everybody submitting their jobs, you will see the list of everyone waiting. So it's quite an extensive list. If you want to look for just your jobs, notice you will just do sq-u, and then you will have a username, your username. It's not here for some reason, but it will show you your jobs. If you want to look for a particular job ID that you have, so every job will get an ID in a queue, you can just do sq-j and the ID, and it will show you the information, current information on your job status. You can also use scontrol, and it will have more information displaying. Again, once you start working with jobs, try running several of these commands to see the result, so you would know which one is more useful for you. Again, unless you try it yourself, it's really hard to describe, but sq is the most important, that displays the queue, and you have also scancel, sinfo, and others. So scancel is if you figure out that your job is actually, something's wrong with it, it's better to cancel it before it even hits the compute node, or cancel it early, because you will be only accounted for how much time it actually ran. So there is no need to sit and wait till the job finishes if you know that there's an error and you want to fix it and resubmit the job. Okay, so important tool that I want to mention additionally is my SciNet. So if you go to my.scinet.utoronto.ca and log in with your credentials, you get a system that will show you all your jobs, previous jobs, and it's updated every like 10 minutes or something. It also shows full utilization, and you can access the job information here. So namely, you can see the performance, how well your job performed. Again, the snapshot is taken only every 10 minutes. So if you're running for 24 hours, you get a lot of data. If you're running only for maybe 20 minutes, you might get only one snapshot. But you do get some sort of information on whether your job is running well. And if you notice there is a drop-down menu here, you can select what you want to look at, CPU, memory, disk usage, and so on. So it's very helpful. I really encourage you to explore it yourself. It's a very convenient tool. We use it all the time. So here's, for example, the job that's currently running, state of running. And as I mentioned here, it also records the script that you used to submit, so you can come back and maybe copy it if you want it. And some of the tips that I kind of mentioned partially. Another thing, apart from writing as a big file instead of lots of small files, is that if you have data that, for example, some matrix, you have a choice. You can either write it as ASCII file, which means that if you create a file on your computer, and you double click on it, and it shows, let's say, a notepad or whatever you're using to display it, and you can read the numbers, 23, 35, and it maybe has spaces in between. This is called an ASCII format. It's the format that you can read. It's human readable. But you also have a binary format, and when you save something in a binary, you open it, you can't read it. There is, like, I know you maybe save some numbers from 1 to 10, but when you open it, there is nowhere near any numbers that you expected to see. So this is a machine readable format. It's a binary format. It's significantly more efficient than ASCII. So when you have 2 terabytes of maybe data, do not write it as ASCII. Do not write it in a plain text format. Write it directly into the binary format that machine uses, because it's faster to write, it's faster to read, and it takes much less space, significantly less space. Plus, when you write something in ASCII, computer has to decode and encode it from ASCII and back into the binary. So it's better just to create binary file, just save it on the disk, and then later when you want to explore, you can access it, and maybe you want to convert it using your code into more readable format. So when it comes to Python, for example, I know many people work with Python. You have pickle format. It's a binary format. Just write it. You have HDF5. You have NetCDF. Excellent formats. Just use them. They're binary format with some additional metadata. So use them to write your information on disk. With RUser, it has NetCDF. It has support for HDF5, so you can use them. Yeah. And you can just write as a binary file. You can open file as binary and just write it directly there. So these are links that are very helpful. If you are first time user or you just started, you feel a little bit confused about the system, the second link of Niagara Quick Start, please read it. You will find it extremely helpful. I found it helpful myself when I started learning about the system. It has lots of scripts, examples that you just copy paste, because we understand that the system is new. Like, this is not something that you usually work with. Your computer has different arrangement of the software, and you might need some help. Just go there and find a script that's appropriate for your particular research. It might be OpenMP code, it might be MPI code. Just copy, paste it, feel free to borrow it. It's there for you. Replace just executable with your executable that you're working with, submit it, and you should be good. Just change the wall time requested, and that's why it's there. It's to help you start running your code. Once you feel more versed with that, then you can adjust and tweak it to your satisfaction. But if you just start and just use examples, they're very helpful. They're short enough, but helpful. So these are just nomenclature. So just kind of definitions and notation that Slurm is our scheduler. So in order to manage this amount of people accessing the system, we are on the scheduler. It's called Slurm. Actually, Slurm is a very complex system, and I think S stands for something simple, which is not simple about it. But anyway, it has even its own terminology. And here you can, for example, see what nodes mean, and tasks per node, CPU per task, and so on. Just familiarize yourself with it to make sure you're putting the right parameters into your job script. I think it's the last one. Yeah. Well, and now it's time for your questions, if you have any. Maybe you already experienced some difficulties and you want us to help you.
You said that essentially like script example.
Yeah. Yeah.
Process log.
Pretty much, yeah.
Or is it software like there are?
Yes, if you go to our, well, let's just go right now. If I go right now to our wiki page, docs, do we have a link to it somewhere? So this is our educational website, and if you go to documentation, so this is our main page, and if you just click on Niagara here, it will give you the overview of the system, how to log in, pretty much what you saw on the slides, but in more just condensed way. You can see here, for example, you have some sort of examples. What else did I see here? Here are the submission scripts. They're very similar to what you saw on the slides. You can copy. So once you see PDF, don't try to copy from PDF. You usually get some hidden symbols. This way you can copy something safely. It's just plain text format. And once you read it, let's say you're curious about R, you just go to here, and let's say you will put R, and it opens about R. We have many users using R. So here you will find some code examples of, for example, how to run an R cluster across the nodes. For example, it needs some tweaking. It's not that straightforward, but you can make it work.
So it's script here, like right.
So, okay, so the way it works is that mobile Xterm is just the tool to connect you to the server.
Oh, so it's like
Well, so the way you think of mobile Xterm is that, okay, what do you have, Windows or Linux? Windows.
oh,
Windows. So when you go to, what is the Explorer? Like, you know, when you have Windows and you click on a folder and you go between them, it's the same thing with the terminal. It's just instead of clicking, you will type a command. You will say cd, basically change dir to this one, and it will jump into it. And you can type, for example, ls, which will list all the contents. It's the same thing as clicking on a folder and just going through the files. This is the same thing. So navigating in your system using mouse is the same thing as going through the terminal, connecting to the remote system, but using commands to navigate through the system. Now, let's say you're on the computer and you wrote a script. So how do you do that? Well, you usually create a file, you double click on it, you have, let's say, Notepad or some system that maybe like environment opening, and you type your code. Let's say you wrote your code in R, maybe RStudio. It will save it in a plain text format. It will just say your code.r. This is your code. You can always open it in just plain text. It means that you open it with Notepad, for example, you can really clearly see. You don't need RStudio. RStudio is just an interface for the convenience. It's not really necessary. You can use any plain text editor. Now, when you copy your file over to Niagara system, you can use, let's say, available editors. We have editors that are available, let's say, VI, whatever you want to call it. Emacs, we have some experts in Emacs. And you have Nano. If you never worked with like a terminal editor, use Nano. Very convenient. You will have shortcuts on the bottom. And very similar to regular Windows text editor. So you will see the same code that you had before on the Windows machine loaded on the system, on Niagara. Now, how do you run it? Well, with R, you need to run rscript command. Let me see. So first you need to, of course, load the modules. You need to install, so when you work on your computer, well, developing something, you install many packages. Well, when you load your R environment, you don't have anything. It's empty, so you have to install them again. So you would need install packages and whatever you're using. So you install, and then you can use, for example, rscript command. So the way you work on Windows, you probably just press a button, RStudio will just run it for you. But actually, you run it through rscript command. So rscript and then the file name of your script, and it will run it. That's how you do that on the system, Niagara, or any remote system, or even if you have if you work through the terminal. So your code is plain text. You can open it and you can read it with your eyes. It's not like a binary format. And the way you run it is you need to tell the system how to run it, because you have many languages. And languages come with their own interpreters or compilers. And rscript is basically an interpreter that will tell the system how to read this code, how to interpret every line. It will convert it into binary format, the one that the machine actually understands. Does that answer your question? Okay, so again, rscript, and then you have a file name, and you're good to go. Yeah, so this is R. We probably have something about Python also. But I think you can here look at the pages. Raj, do you know where the, like you can see all the pages? Okay, well, just give it a try here. Just search for Python, for example. And it actually gives you already suggestions. So you have Python. We have optimized Intel Python as well, how to create environments. Please do use environments, but not conda environments. Again, familiarize yourself with Python. If you're working with a particular software, even if it's MATLAB, like if I will type here MATLAB, you're really curious how to run it, right? So you would just do MATLAB. And there is a page. And it's the first thing it says not using MATLAB. So please don't use MATLAB. But if you really insist, there is a way, kind of. So what is, oh yeah. What's available here? Again, so if you're using particular software, type it in the search field, and it might give you some information, including the examples how to run it. Good? Okay. Any other questions? This one?
Yeah. Suppose.
Yeah.
What is mean of
Export? Where is opening?
create
This one? Export? Okay. So when you work with Bash, so Bash is its own language. So the way you, so what do you say? So when you connect to the remote system, the commands you're actually running in a terminal. But this terminal also has kind of a language, its own language. And the commands that I mentioned, cd and ls, they're just the commands that being interpreted into particular commands that computer understands. So you're not talking to the computer with computer language. You're talking actually with English language. And English is being interpreted into something that computer understands. There is no way you will be understanding what computer. It's just zeros and ones. But we communicate on a higher level, and we create abstractions. So when you type something, you're typing it kind of in Bash. So this is called Bash, and it's a shell language. It has its own syntax. And export is one of these interesting keywords. It allows you to create, oh, I can actually edit. Oh, how interesting. I better not to. It can create a variable. So you guys familiar with variables? If you coded before? Variable, yeah? It's just the placeholder, like you want to put a value there. So the way you define a variable in Bash, you can use an export command. So this basic line means that create a variable omp num threads with the value of this particular. This is another variable that is created by Slurm, by our scheduler, and it would be taken from here. So you can see how it says Slurm CPU per task. Whatever you put there, whatever you put here will be just transferred here. So if you put here 20, it will be 20 here. If you put 40 here, it's 40 here. So it means you're creating a variable with the name omp num threads equals to 40 in this situation. How many threads it's going to use? Yes, because when you program OpenMP, it expects this variable to have number of threads. If it doesn't have anything there, if this variable doesn't exist, it will just use the default amount. This will default the number of cores.
So if I have a variable to one.
Yes, so if you do omp num threads equals to 1, you have serial code now. It means there is no parallelization. There is nothing runs in parallel anymore. Everything is sequential because it's one thread. So you just, instead of hiring 10 people, you hired one person. Well, how much one person can do? Like one task at a time, right? But if you have, let's say, 40 people working for you, you can give each of them a different task. and you have parallelization now. You have a faster result. Well, assuming your workers work properly and you give them proper tasks. Again, just you shouldn't think that parallelization just change it from 1 to 40 and everything works. You have to be aware how your threads communicate between each other, and is it really, maybe there is a racing condition, meaning that, let's say, a couple of your workers are trying to access the same resource. Simply that if you have 40 people trying to access one book at the same time, you might having people tearing out the pages out of it. So it's a shared resource, and you have to be sure that it's accessed properly. There is, you can actually specify as many as you want, but then you will have problem that it's like you having 40 people, but you're giving them 20 tasks each. So now you have so many people working on so many tasks, and what you want to do is basically make each thread work on one task at the time. And you have 40 cores. So let's say you use 40 just as a physical example. So this is your maximum. So you would use 40 threads for 40 cores. If you will ask for, let's say, 500 threads on 40 cores, you will just have threads stepping on each other toes, and you will get actually slower performance. It's what maximum makes sense to use. Well, you can use 80 because it has hyperthreading. Again, it depends on your project, because so the idea is that you can allocate as many threads as you want. In fact, you can ask for as many threads as you want. It's up to the system to give it to you, because you politely asking, give me please 500 threads. But if the system decides that no, you only get 3, you get 3. This is an interesting thing with OpenMP. You're not guaranteed to get as many threads as you're requesting. However, you can request for 500. Is that maybe you're requesting for them, but you're not using all of them at the same time, because you can arrange your code in a way that you will be using 100 threads, let's say, to do one thing, and then you will be waiting, you will be structuring your code, that other 100 threads will do something else. So you're not limited to how many threads you're asking. It just makes sense usually to use as many threads as you have physical or logical cores available.
So the CPU cores that
So CPU per task is how many threads you're asking for. So it should be related to the number of cores, but again, if you very familiar with OpenMP and you feel confident enough to play with the code, you have a complex code, you might use less number of threads or more number of threads. Like, how many workers do you want to perform your calculation?
last question. I have seen in this document most that in the plan for
Maximum nodes? Oh, it's on debug partition. So you have login nodes where you have 6 available anytime. You can jump between them. Then you can request up to 4 nodes, up to 4 nodes as a debug job for 15 minutes. In fact, if you use a particular command, you can get many nodes as a debug in a debug partition. It's just usually you don't need more than, let's say, 2 or 4 to test it. And you want to do this for the short time because it's just a preparation for the next step, which means submitting a large job. But on a compute node, you can get up to 1,500 nodes, up to 1,000 nodes, whatever you want. It's just remember that you usually, if you have default allocation, you will run out of your allocation very fast if you start using a lot of like a massive number of nodes, because you will be charged, not like physically, you will be accounted for it. It means next time you're running something, you will be waiting for 3 days to your job to run if it's maybe an hour job. So the more you're using right now, the longer you have to wait later. If your PI has an allocation, then it's different. However, people also overuse sometimes their allocation. They run a lot today, tomorrow, and then they're submitting asking why it doesn't run. Well, because you need to wait a couple of days for the allocation kind of to go back to regular usage. So sometimes people see that they're using heavily this week, and the next week they can't use anything. Well, you have to wait a little bit. It will stabilize itself. Okay. Any other questions? Once again? What's the difference? Okay, so these are two different protocols. So OpenMP you want to use if you have a machine with multiple cores. So your computer might have 2 cores, right? If you have 1 core, doesn't make sense. You have serial code, OpenMP will just run serially. But you can request multiple threads, it's just that one computer will have to switch between them. You're talking about taking, let's say, 2 cores and running completely in parallel 2 different, or just, you know, the task is divided between 2 cores. Now this is OpenMP. It's all about shared memory. It means that all the threads on your machine will have a common memory. They see the memory. So you can put a variable and it could be accessed by both threads. Let's say if you have 2 threads. Now MPI protocol is a communication protocol between 2 machines. So in fact you can have a machine with 1 core and another machine with 1 core, but you want to connect them, and through the internet, for example. And in this situation, you can run one computation on one machine, another one, and then you can combine them together. So this is MPI protocol. And MPI protocol has different implementations. So OpenMPI is just one of the implementations of the MPI protocol. So people came up with some rules of how to perform this kind of calculation. And different companies and different groups came up with slightly different implementations of these rules. And you have different implementations like OpenMPI, you have Intel MPI, you have MPeach, and so on. They're just slight variations, and you will be using the same commands, but you might get different performance by using different implementations. So and then you have a hybrid code, which means that, let's say I have 2 nodes with 40 cores each. So Niagara situation. And I would like to take a full advantage of it. Well, I have several choices. So first of all, if I want to run something on both nodes at the same time, and let's say I have an object that's shared between them, so they're not completely separate. Because if I have completely separate tasks, I can just run them in parallel, and there is no communication between the nodes. They're completely separate. For example, you have files, and one process, let's say you have 2 files, right? And one just node is reading one file, and one reading is another file, and there is no communication. Completely separate, perfect. It's called embarrassingly parallel. There is no communication. It's very fast. It's the fastest way. However, if you know that there is a communication between them, let's say one task is performing something, you need to update something for the second one to continue, this slows down usually the whole thing. That's because there's a communication between the nodes. And you can either run it on one node, and then you will use OpenMP, for example, or you can use MPI, but you will run 40 different processes of MPI. So the way MPI works is that it creates multiple processes. They're all kind of independent. They don't share the memory. So OpenMP shares the memory, but OpenMPI doesn't. It means that if you have 2 processes running on one machine or on 2 machines, you have to explicitly state, take this matrix, take this value, and send it to another process. And then let's say send it back. So you have to manually control this communication between the processes. It's quite laborious. With OpenMP, you have to do that. You just say parallelize, and it works. So this is a very good, simple way to parallelize your C code, for example. It works with C and Fortran. Now, when it comes to MPI protocol, you have to explicitly state what is shared, what you want to send between the processes. Now, you can run 2 processes on one computer, or you can run one process on each machine, and you have 2 machines. Now, let's say you would like to take advantage of full 40 cores on each machine. So what you can do is that you can launch one process on one machine, another one, and then within each process you can run OpenMP code. So now you're using 40 cores here and 40 cores here. In total, you're using fully 80 cores available on 2 nodes, but it's up to you to implement it. It's called the hybrid code, which means you launching one, maybe you want 2. It really depends. The performance varies based on combination between MPI processes and OpenMP processes. Some hybrid codes are, like, it really depends how well you can split the tasks between your processes. Sometimes we saw some software performs well just if you launch 80 MPI ranks, so MPI processes. In this situation, it will just, let's say, take 40 MPI ranks on one, 40 on another one, and it's completely running, it's running well. Or you can do, for example, 2 MPI ranks, one on each machine, but each of them will be running 40 core OpenMP code. Does it make sense? So there is a difference between OpenMP and MPI on OpenMPI. OpenMPI is just an implementation. So don't think on OpenMPI it's the only thing. You need to think of MPI. So you have OpenMP and MPI. MPI actually stands for Message Passing Interface. It's communication between the processes. So you have OpenMP and MPI. Now MPI has implementation Intel MPI and OpenMPI. That's what's available on our system. Okay? So OpenMPI is not related to OpenMP whatsoever. It's like different technologies, protocols. Good? Okay. Anything else we can help you with? Good. Okay, so this time we don't have a snag meeting, means no pizza. But we usually have pizzas on snag meetings, so just if you have any questions, next time, I think will be in January probably, we might host one. So we host Intro to Niagara all the time, but you guys now experts in it, so you don't really need it. But you still can come on a snag meeting and listen to maybe one of our presentations. Okay? Well, I thank you for coming. And remember, support at SciNet, our email. Just email us if you have any questions. We have lots of courses. So just check out our website. And if you would, you can just drop by. And if you find someone in the office, which we usually are, except from 23rd of December to 6th of January, please just ask us and we'll help you. Okay? Well, thank you.
Fantastic. Thank you very much. Appreciate it.
You're welcome. You're welcome. Okay, that's enough. Oh, look, this one has a stop button, a pause button.
Oh, does it? Oh, no, nice.
Yeah.